Live?
Yep.
Are we live?
Yep.
All right. Oh God, where's the camera?
Over there.
Oh, hey, hi. All right. Welcome to the Physical Geography 2 Midterm Review. I am Mr. King, and we have...
Non-Dexter.
All right, and we are going to go through each one of the labs step by step and go through the important points that you will need to know for the midterm. So what we're going to do is Dexter and I are going to break down some of these labs for you, and I believe we're going to start right at the beginning with Lab 1, Map Essentials. Do you want to do this one or me do this one?
I'll do the wrong ones.
Okay.
Yep.
All right, and I'm going to step you through some of the map labs. All right. So when we talk about maps, we are talking about something that shows a spatial reference. So a map, as it is defined, is a representation of Earth space to map space. That is a very important definition to know. It's a representation of Earth space to map space. So basically what that means is we're showing you a broken down image of a selection of the Earth's surface. And maps have many different ways to
You can go on this right now.
All right. So, maps have many different things you need. So for let's say an essential map, a stereotypical map, you need as many of these 8 things as you see listed on the screen here, as you possibly can have. So first off, you need a directional reference. These are something that seem kind of, I don't know, like knowledge you would know where north is, right? When you look at the United States, you know where the northern part of the country is, you know where the southern part of the country is. But this is not always the case when looking at other areas on planet Earth. So a directional reference is very important. This typically takes the form of a north arrow or a compass rose. So additionally, you know legend or a key. So the legend or key is very important because if you have information with which to show, and I think you can see a map of Africa here, and the key is very important to show you the information that it is trying to present. And in this case, this is population density, so this is persons per square kilometer, and it is showing you the scale, as you can see the different colors of red here, the scale which shows you density. So the legend and the key is very important for showing you the information on the map. So, third, we have a source. This is one where any of my students will know I spent a good bit of time talking about the source because the source of maps is very important, especially when we come to points of a thematic map. We talk about the reference for thematic maps. When you have a thematic map that might be talking about a voting areas or what might be some political maps, right? We spent a good bit of time talking about this. If you remember, on day 1, we spoke about how when you are looking at election result maps, it's very important to see where these are. And that also leads us into the next part, is the date. The date is very important. So again, I use election maps for mine because they have a lot of things that we can kind of like harp on for maps. So not only is the source important, but the date. So if you're looking at a map that shows a result of something, and you see that you're like, wow, this looks like, I don't know, this third party won out in a landslide, then you realize it's a map from like 1932. It does not show you the information that is relevant to what you are doing unless you are studying that particular point in 1932. So, again, the next part, number 5 here, comes back to the source. The name of the cartographer. A lot of times, when you see a person's name on a map, it's the same thing as when you look at a painting and you see a signature down the bottom, or it's hidden somewhere within the map. It is just a way for the cartographer to say, this was my map, I did this. But also can give you an idea, can feed back into the source of the map. So, give you an idea of who has done that. Also, projection number 6. When we talk about projections, we are talking about the way that the Earth is projected onto a flat surface, right? So if you're looking at a map, it's a flat surface, Okay? And what that does is when you start taking a spherical or oblate spheroid, as our planet is, and you flatten it out, you start to mess with some of the ways that Earth space can be projected. So the map space will be maybe what you want it to be, but it might not be accurate. It might not be accurate to what the Earth space actually is. I think we're going to come back to that one, but we're also going to talk about 7. We're talking about scale. And scale is really important. This is another one that we spend a good bit of time talking about. And scale, right, is you usually see as a bar on the map. So in this one, you see in the bottom right corner, you will see the scale. And it will tell you that a certain distance on the map is that much of a distance on Earth, actual space, right? So in this one, we have an entire continent, so of course our scale goes up to 1,000 miles. I believe if you were to put that down on an actual map, it might be like 1 or 2 inches is 1,000 miles. So the scale gives you an idea of how much space exists within a measured area on the map. All right. And then we have a locational reference. So a locational reference can take many different forms. In this case, we have what are the lines of latitude, longitude. Remember, students, that those lines of latitude and longitude, we call that a graticule. Okay? Those lines of latitude and longitude are our locational reference. And one of the things you know, if you're looking at Africa, you also know, I'm not sure, I can't get a quite good look at this, but the equator runs through Africa. So that is another locational reference. Hopefully the prime meridian does as well at some point through Mauritania and Liberia, I believe. All right, so we have that. Before I move slides, are any questions so far? Anything? No? Okay. All right. So let's break this down just a little bit. We're going to go through these and hit the important parts here. So the legend or the key, so it shows you areas that are important to note on the map. And you can see that they are typically simplified. So if you have a town, right? Let's say you have the town of Anniston or Gadsden, which Jacksonville is kind of in the middle of. On a map, they will be symbolized the same way. Their population is roughly the same, the town size is roughly the same, and we will typically symbolize those with usually a mundane little dot. And then if you are using something like a capital, right? Usually you will have the circle with the star in the middle. That shows you that that's the capital. That is a universal symbol for the capital of a sovereign region. All right. So yes, it tells you that the symbols are generic pictures drawn to represent real objects. So you might have, you might see the symbol of a cross for a church, or you might see the symbol of train tracks for a train depot, and it will give you an idea of what is there and usually be somewhat intuitive. So, all right. So typically, you cannot show everything on the map. That is something that we touch on here on the slide. Is you may be in an area where you know your house is there, but you can't exactly map your house. I mean, you could. What about all the other houses? There's no way to feasibly pack them all in on a map, especially when you're looking at an area like we looked at before, which was as large as Africa. There's no way that you can pull out one single house. Okay. So that is a legend. The legend shows you in graphic form, the features of a map. So we did this with the USGS topographic symbols. And we had the pamphlet, and you got to see the different varieties of objects on there. All right. So now let's talk about projection. I like to talk about projections. Projections are cool. There's some really cool projections out there. If you really want to go down a map maker's rabbit hole, just go on Google and type in really cool projections. But we start with the most important part and what is a base of the geographic practices. Is that the Earth is round. The Earth is round. It's not flat, regardless of what some people say. Just so you know, the Greeks 2,500 years ago knew the Earth was round, and we still do today. So, But how do we properly show the Earth on a flat surface? And this is where projections come into play. Because the goal of any projection is to properly preserve the shape and scale of the landmass. Right? But it tells you, and the third point here, is that it is nigh impossible to do so. There are a few that come close. There are a few that come close. There's a projection called Dymaxion. Dymaxion comes shockingly close, but if you were to take a Dymaxion projection and try and cut it out and make a map out of it, well, it would be kind of weird. It'd be very jagged and lots of like strange ends. So the projection is what happens when you take a piece of paper. Let's say you took a globe and a piece of paper and you put the piece of paper on the globe, right? So you are getting a projection that is based on that piece of paper. Typically, what you will see in most manuals or books is Mercator, but we don't do that here. But there's no such thing as perfect projection, and there are some that are more applicable or easy to use. But typically, they all have distortion. And in this case, we have distortion in three ways. Three types of distortion. Is your distortion in direction, okay? Your distortion in area, and your distortion in shape. So I will leave the next couple slides, we're going to get into that. So, distortion in direction. So we talked about distortions in direction. We can look at the globe, right? And you might say, well, the closest path from here to, let's say you wanted to go visit London. Right? You would say, well, that's okay. Let's say you leave from JFK, you're going to London. And it's a straight line. Well, no, that's not actually the shortest path. The shortest path is actually to follow the natural curvature of the Earth, which takes you a little bit farther north. And it gives you this arced path that takes you up near Greenland. So, distortions in direction are important because if you were to draw a straight line between 2 points at separate ends of the Earth, you would actually be adding travel time. If you were to travel down that line, you would be adding a great deal of travel time because you would not be accounting for the curvature of the Earth. So most maps have some form of distortion in direction. This is one of the most common forms of distortion. This is distortion in direction. All right. Now, distortion in area. I like this one because this shows the two things on a map that typically get distorted the most. Africa is often a culprit here, but Greenland and South America are really, really big culprits when it comes to distortion in area. So, the question is, why is there distortion in area? And the answer to that comes from the fact that as the curvature of the Earth, as you start to get further away from the equator, that curvature of the Earth, as you try and map that, you start to see that the objects start to get closer together on that if you were to take that piece of paper, right? And so therefore, some of your objects that are further away from your central point will appear larger or smaller. And one of the things that we talk about in my class also is map bias. It's map bias, and one of the things that we as people who live in the Northern Hemisphere, a lot of our maps are biased towards the Northern Hemisphere, so it distorts shape, especially in South America, where you will see, so we can see more area in the Northern Hemisphere, okay? You will see that those areas will appear larger, and South America will appear smaller, okay? Because we have a map bias, right? But Greenland has a great bit of distortion due to area, due to the fact that the Earth, when you start mapping that part of the Earth, it starts to curve. And it almost stretches out the shape of Greenland. And makes it appear much larger than it actually is. If you are looking at certain projections, there are some that actually are much smaller than it actually is. But Greenland is one that is very difficult to get an accurate size or idea of how large the landmass actually is. So remember, the distortion in area occurs, again, just like direction, because of the curvature of the Earth. Because it is difficult to take a curved area, a curved surface, and put it in something as flat as a lab manual without messing some kind of scale or stretching it without messing it up. All right. Let's talk about distortion and shape. Distortion and shape and distortion in area are often talked about together. When we talk about distortion and shape, one of the things I like to touch on is the shoreline paradox. That if you were to try and measure a shoreline, and you were to have multiple teams try to measure a shoreline, each one of you would most likely get vastly different answers. Because it all depends on where you are mapping it from, what path you are taking. And in this case, as you will see this map here is greatly distorted. This is not a map that you would use for most things. This map here, I believe, would probably be shown for, I don't know, the oceans aren't that distorted, but. So you sometimes have areas, and we come back to Greenland yet again, where we have that distortion in shape. Sometimes it stretches out. We also get this, one of the other culprits here is when you get to the Bering Strait, where Russia and Alaska are mere miles from one another. And there are some maps, especially on the globe I noticed this, where the shape isn't quite right. It is like moved a little bit because of the curvature, and that sometimes is to account for corrections in the map. Some areas you will need to sacrifice that. But distortion in shape goes hand in hand with distortion in area, because again, we come down to trying to map a flat surface with a curved shape. Okay, so somewhat scale. Any questions so far? Good. All right, so about scale. So talk about the RF. The RF is representative fraction. And when we talk about representative fractions, remember that when you see 1 to something, you see 1 to 24,000 here, right? Representative fraction, and it is presented as a ratio. And what is a ratio but a fraction? 1 of something else, a number to something else. And this is a very useful way to look at a map. And one of the things that is sometimes difficult to wrap your head around is that a representative fraction, you can measure the RF with anything. You can measure the RF with anything. You can measure it with lab manuals, you can measure it with pens, you can measure it with keyboards. But what that's telling you is if you were to put the keyboard to the map, that there is one keyboard that fits on the map, and 24,000 of those will fit in the space that that takes up. So, let me review this one more time. So if you were to take an object and put it on a map, so let's do the lab manual this time. You have the lab manual on a map. What the RF tells you is that one lab manual on the map equals 24,000, or whatever number comes after the 1 that is at the bottom of the fraction or the ratio. In this case, 24,000. So one of these equals 24,000. That's what that tells you. So always be sure when you're looking at the RF to know, and you will see it has no units. It has no units. This is how you determine the RF from another scale. It has no units because units can be anything. Units can be anything. All right. So now, unit conversion. So you'll need this. I'm not going to go too far into this because this is, yes?
Will we have to differentiate between the scales on the midterm?
I believe we will have RF and verbal or graphic. We will. There will be 2 different scale questions. Let me see if there's another. Let's see. Whoop! I went too far. It's fine. Here, we're going to be back. Yeah, there we go. We're checking on that, but this is a good thing to know. It's a good thing to know that the RF, if we're talking about graphic scales or another scale, it will tell you, you will typically see one distance is equal to another distance. Let me hear what Dexter has to say before I give you a...
Looks like we're only using RFs, and they just have to convert into different units.
Hey, all right. So we are only doing RF. We are only doing RF. Awesome, thank you, Dexter. So, you will have to convert I believe this will be supplied to them. I think I'll probably give it to my students, but I think.
Either that or calculators and stuff are allowed. So
Okay. So just so you know, you don't need to know this. You don't need to memorize this. We're not asking you to do that. We're not asking you to memorize the chart here. So, all right. But there will be unit conversion. There will be unit conversion. So what this is going to tell you, you will see that a map is a scale of 1 to something else. And then we will say, here are how many inches you measure on the map. So remember that 10 inches, right? If you measure 10 inches, that means that there is a number on the map equal to the ratio. Let's break this down. So when you're looking at this, what you're going to do is, if you have a 10 inches, right? So to a 1 to 75,000 map, you're going to multiply the 75,000 by 10, right? But then we complicate it, as science often does, and we say, hey, how many miles is this? Well, you're going to have to convert to figure out how many inches are in a mile, okay? And then divide by that. And it will give you your answer. So you will see that 10 inches on the map, on a scale of 1 to 75,000, is 11.83 miles. Okay. To put this in, this is basically like cross multiplication. Okay. So be sure that you multiply both sides by the same thing. Multiply both sides by the same thing. So take your scale, multiply both sides. So say 1 to 75,000 and 10 inches. You want both sides to be equal. Right? And then you're going to have to divide by the number of inches that are in the distance that we are asking you for. And yes, you will have to come back to this neat little chart. All right. Any questions before Lab 2 begins? Should I keep going with Lab 2? Yeah. Okay, all right. Any questions for Lab 2? All right, let's talk about topographic maps. So we're just going to briefly touch on this. I believe there are.
I think there's only like 2 or 3 or so questions on maps on the midterm check.
Yeah, very small part, but we're going to touch on this. So remember, topographic maps are a way to show you information on a map, and we specifically see this with. Bring it up here. Yeah, we remember this. Yes.
5.
There are 5. Okay, so this is a part of it, but we're going to talk about this. So this map should look familiar to the entire class. So this right here is part of the Jacksonville quadrangle. I think I can tell this is the northern half. Yes, this is the northern half. So I'm actually going to crack the lab manual for this one so we can discuss. All right. So remember the first thing we did when it came to this was we looked at the map and we were given locations. Can they actually see this? Yeah. Okay. So I'm sure I was gesturing to something. Look at this. All right. So you will see that we had given you locations. So I believe the first one we did was Martin Hall, and we had asked you to find it down to the nearest 30 seconds. So what you're going to do is you see, remember, seconds are the 1 tick, right? Right, where minutes are the 1 tick, seconds are the 2 ticks. But you want to go find the minute, break it down, because you know you won't have multiple degrees in a map like this due to the scale. So you will see that there are guidelines here. So you will see 50 inches, right? And up top, or 50 minutes, sorry. And then up top you will see 52 minutes and 30 seconds. So what that tells you is if you're looking for, let's say, Sulphur Springs, you know that it is between 33 degrees and 50 minutes, and 33 degrees and 52 seconds, and 52 minutes and 30 seconds. You know it's between there. But this is where things get complicated. Because there are no little extra tick marks here. So this requires just a little bit of guesstimation. Little guesstimation has to go in here. So you look at the other demarcated lines here. Now some of these are red, we're going to come back to those. Don't worry about the red ones right now. But you will see that there is other black lines. Right? And that is showing you areas where the minutes change. So you have 50 minutes, and this one is 51, the one towards the middle. It is a little bit, if you are looking at the actual PowerPoint slide, it is a little bit above the blue circle, right? So you know it's somewhere in there. So it's 50 minutes and 51 minutes, and here's Sulphur Springs. Now you'd say, it's like halfway, a little bit more. So you might say 50 minutes, and I generously say 30 seconds to do the trick, right? You could do that. And I will tell you that on the midterm, when you do these questions, we are not going to be super strict, like how dare you not get it down to the second. We're not going to do that. We're going to be fairly lenient, but we want you to be close. We want you to be close and use the context clues on the map. And we talked about this in class. The context clues are very important. So be sure you watch. So here's 50 minutes. It's circled in blue, right? And these black tick marks show you where the minutes change. Okay? All right. But then we, of course, overcomplicate. Because maps show a lot of information, and you would be surprised how much information you can pack into a map. And if you remember, I know this was the second week, this was a while ago, we talked about the USPLS system. And we talked about how the USPLS system has been around since 1798. So this is an ancient, archaic system, but it still works. It does still work. And what it does is it breaks it down into these squares. And on the map, you will see these red squares. You'll see these red squares, right? And you will notice that they have marks showing, I don't know, when you look at them, it's kind of weird. You're like, oh, well, R7E, R8E. Okay. So we break this down. We do it into tiers and ranges. Tiers and ranges. So, the tier you will see. So tiers, yes.
One more question.
Yes.
Will we have to convert from minutes to seconds to degrees?
They don't have to do decimal degrees.
Not for this. Yeah, not for this one. There won't be DMS to. There won't be degrees written seconds to. Yeah, we don't do that.
Yeah.
That's what this is. Okay. You will not have to do convert from degrees written seconds to decimal degrees, or vice versa.
Double check though. I'm pretty sure we don't, since we don't in the actual exercise.
Yeah, I didn't teach it, so I mean, I hope that's not in there.
We do that too.
Yeah. A good question, thank you. So continuing on, we are going to look at the tiers and ranges. So I'm going to try and not complicate this, but think of tiers as lines of latitude, right? You will see tiers running laterally across the map, right? Sideways. So you see where the blue circle is, and it runs the whole way across, okay? So tiers are like latitude, okay? Ranges are like your longitude. Ranges are like your longitude. So you see the blue circle at the top, okay, is R7 and R8. And pay attention to the location because this tells you that everything to this direction is R7 and everything to this direction is R8. And this is the same as a demarcation between a line of longitude. So when we do tiers and ranges, we're basically looking at latitude and longitude again. And of course, we're going to get more into that, but that is how this starts. So you are going to write it down. When you write these things down, you are going to do, just as we do with latitude and longitude, you're going to tier, right? Tier your latitude, right? By R, your longitude. Okay. And we further got into, and here's one where you will have to break it down into sections. So we continue, and you break it down even further into sections. And what you're going to do is you're going to look at the number. You'll see a number, 6, 5, I think, is that 32?
Yep.
That's quite the jump. So, listen, this stuff does its own thing. But you need to pay attention to the numbers because this is the section that it is in. So you will do tier, latitude, right? Tier, range, okay? And then the section. And it is the part at which they intersect. That section is going to be third, okay? Beyond that, I highly encourage you to read page 15 of your lab manual and talk about quartering. It's very difficult for me to get into, I don't think we do, very difficult for me to get into quartering here, as we do not have the maps in front of us, we don't have that tactile, that we have to sit down with and actually start measuring it out. But we get into quartering where you can actually start breaking down those squares into their own, essentially, ranges and tiers, right? And you get into what I believe is you get down to acres. You can get down to certain areas where the acres are shown, and even show you what point they are at. Again, I highly encourage you to read page 15 in your lab manual, as that is the last part here. That is more of the tactile experience of this. You're going to sit down and actually do. And I think that's the end of that. So remember, tiers, latitude, ranges, longitude, and sections of the intersect, where they come together. And I believe that is all I'll be back for live thought. Oh.
Alright, before I get into Lab 3, Igneous Rocks, is there any questions on Lab 2?
No questions in chat.
Alright. Alright, so now we're going to get into Igneous Rocks. You want to follow along in your lab manual, which you can access through Canvas. It'll be on page 19. So there's a few ways that we can classify igneous rocks, and that is through their texture and composition. First, we need to know the difference between texture and composition. Texture essentially means the size of the crystals inside of the rock. And then composition means its chemical composition. So we have a few textures listed right here. We have phaneritic texture. That means that the rock is made from magma that cooled inside of the Earth's crust. And due to it cooling inside, crystals, or the crystallized structures that compose the rock, have time to grow. So they generally have larger crystals. In further slides, we'll have examples of different rocks, and I'll tell you whether or not they're phaneritic or aphanitic, stuff like that. So, kind of the opposite of phaneritic, we have aphanitic. These rocks are created from lava that extrudes through the Earth's crust, and so they have less time to cool because inside of the Earth, there's kind of some insulation from other rocks and materials that helps the magma stay warm and for crystals to grow. When it comes outside of the Earth, it doesn't have that insulation because it is exposed to the elements, possibly to water, stuff like that, and so the crystals do not have time to grow. So aphanitic are extrusive rocks, and crystals cannot usually be seen by the naked eye. Next we have glassy texture. If you remember from in class, the only glassy texture rock we interact with is obsidian. So it has no crystals and has a glassy feel. If you slam the rock on a table, it'll break into shards just like glass. And they are typically made from when magma is extruded into water, and so the magma, which then becomes lava because it's extruded, it cools immediately. No crystals have time to grow, and that's how it gets its glassy texture. Alright, before we get into porphyritic and pyroclastic, do we have any questions in chat?
Nope.
Alright. So next, we're going to go over porphyritic, and we'll go a little bit more in depth with showing examples of these textures once we get to that. Porphyritic rocks are crystals encased in ground mass. So magma contains different types of elements in order to produce a large variety of different minerals. Different minerals crystallize at different temperatures. So as magma begins cooling inside of the earth, the high temperature minerals, which are the ones that melt the last, they cool first. And so we kind of have this order of operations in the crystal cooling. And so first the larger, or not larger, but the crystals that form or melt at a higher temperature, they start to cool, form larger crystals, and then you go next down the line to other crystals that melt at a lower temperature. And so this partially crystallized or partially molten magma, when extruded, it begins to cool rapidly. And so the rock texture is called porphyritic, where large phenoses, which cool rapidly, or which mean big high temperature crystals, are encased within a matrix of low temperature aphanetic crystals called ground mass. So if you think about it, porphyritic is kind of a mix between the phaneritic and the aphanitic, but it is its own class. And next we have pyroclastic. So pyroclastic, it literally means fiery chunks, and that happens when a violent or volcano eruption happens and it shoots magma out. So examples like scoria and hummus that we will show, I believe they're in this PowerPoint, have these little veins and holes in them called vesicles. That happens due to the gas released from the magma as it is violently extruded from the volcano. The gases escape, make these veins called vesicles, and also some contact through the air makes it cool really rapidly as well, so they don't get to form back together and close up. Is there any questions on the textures right now?
In chat.
Alright. There's not a slide on composition, so I'll just go ahead and get into it. So magmas are very intricate and very tremendously in composition, with the potential to form hundreds of different minerals. In spite of this enormous complexity, we typically only go into 3 different types of magma. Alright, so the first type of magma that we cover in class is Felsic Magma. Felsic magmas are high in silicon and low in iron. So the question asks, what does rock, or what is rock's E composition? We're looking for either felsic, mafic, or intermediate, one of those 3. And then when we ask for its chemical composition, it's essentially asking you to break it down a bit more. We want to know what it is majorly made of. So for felsic's case, it means it is high in silicon and low in iron. These rocks tend to be lighter in color and lower in density, often producing rocks that contain a lot of quartz. Next we have Mafic Magma. So Mafic Magma, you can think of it as the inverse of felsic. So they are high in iron but low in silicon, and they also produce rocks that are darker in color and higher in density. They contain little pores. Next, we have an in-between, a middle ground between the magma. We have intermediate. So these magmas are between mafic and felsic in composition, and the resulting rocks fall between those two types in terms of their physical characteristics. If these rocks have big crystals, about half of the crystals will be white and about half of them will be black, and if they contain really tiny crystals, the rock will be grayish in color. Before we get into specific examples of these textures in compositions, do we have any questions?
No.
All right, so I went ahead and went to the next slide. Right now we have gabbro pulled up on the screen. So gabbro is a mafic phaneritic rock. So that means it is high in iron content, and with it being phaneritic, that means it is an intrusive rock. We can tell that because of the large crystals. On this rock, you can see the individual crystals. Doesn't really show that well personally for me, but you shouldn't have lighting issues on YouTube, so you should be able to see the individual crystals. But sometimes, because gabbro can be so dark, it's hard to see the crystals. It often helps to turn the mineral in a light so you can see the reflections, but we aren't going to be really working with rocks anymore in class, and you shouldn't have to identify with pictures in the midterm anyways. So next we have granite. Granite is another phaneritic rock, but it is felsic. So it is higher in silicon and it is intrusive. So it is primarily composed of quartz and potassium feldspar with other specific minerals, or mafic minerals like biotite, but these minerals are large enough to be identified with the naked eye due to it being intrusive. Next, we have basalt. Basalt is the chemical equivalent of gabbro, so it is a mafic rock as well. The only difference between basalt and gabbro is that basalt is an aphanitic rock, so that means it is extrusive. It cooled on the surface of the earth. And because of that, it looks darker in color because the lighter crystals didn't have time to form, so oftentimes it is black. Next, we have Corporatic Rhyolite. So this rock is cooled down in two distinctive stages, producing two distinctive crystal sizes. The large phenosis of the feldspars are formed when the magma was cooled slowly beneath the surface, and they're encased in ground mass of aphanitic crystals, which are produced when the magma is carrying the large feldspars onto the surface of the earth. And as you can see from that example, you can distinctly see the crystals of the more mafic rock, but as it was extruded, it is more felsic. And since it is primarily silicon in composition, rhyolite is categorized as a felsic rock. Next, we have obsidian. So obsidian is similar in composition to both granite and rhyolite, so that makes obsidian a felsic rock. But you might be thinking, this rock is very dark in color. How is it not, at the very least, intermediate to mafic? That is because it cools so fast due to probably going into some water, like an ocean. The impurities, like the feldspars, or not the feldspars, but the biotites or feldspars darken the color of the rock, and that's how it gets its distinctive dark color. Fun fact, the Aztecs used to use obsidian as arrowheads. Next we have humus. Humus is a pyroclastic rock produced by gas fizzing out of extruding magma. So humus is usually silica-rich in composition, so it is a more felsic rock, and it produces in relatively sticky, thick lava. The gas bubbling through this sticky magma produces a foamy head, much like found in soda or beer, and when this rock cools, it solidifies and forms humus. There are very many small vesicles in this rock that give it a low specific gravity, so that means it is very light, very not dense, and with some samples you can set humus down into water and it will actually float. Guess we have obsidian again. Do we have any questions about rocks? Next, we're going to be getting into sedimentary rocks. So, sedimentary rocks are essentially rocks made from rocks. So, they are created in 4 distinctive steps. First, the rock is weathered to produce sediments, which are small fragments of rocks or dissolved ion. And weathering can be broken down into either mechanical weathering, which means a physical force has physically touched the rock in order to break off small pieces of sediment, or through chemical weathering, which is some acidic type of liquid. For example, limestone, if rain falls down into a cave and goes over limestone, eventually the acids from the decomposing plant matter melt down the limestone a bit, but not really. So it takes some of the calcium carbonate and then transports it somewhere else. And we'll get into that with transportation. So that's the next step. Transportation essentially means it takes those sediments and puts them somewhere else. And that can be done, like I said, with the limestone of rainwater leaking through a cave to dissolve the calcium carbonate ions, or, for example, a river, a stream, a creek, stuff like that. So next we have deposition. Deposition is essentially where the sediments end up. So we touch on deposition more in depth in historical geology, but not really that much here. But deposition essentially happens when the water or whatever is carrying the sediments somehow stops, either by going from a river into the ocean where the water loses velocity, or where in an ocean basin, or, for example, my limestone example, where the rainwater falls down, kind of goes over some limestone to steal its calcium carbonate ions, it ends up somewhere else, and that kind of goes into the next step of lithification, but the water tends to evaporate away and leaves the calcium carbonate behind. Another thing about transportation, when we want to look at the sediment types or these particle sizes as well, higher velocity water or wind is required to move denser, bigger sediments. If you remember us talking about sediment sizes, a high velocity river would have to take gravel away, and then once it loses velocity, the gravel kind of falls off first, and then as it loses more velocity, then sands start to fall off, then it loses more, then silts start to fall off, and then lastly the clays fall off. And that is an example of deposition. And for the last, lithification. So sediments lithify, which essentially means to turn solid because lith means rock, so lithification means to turn into a rock. So like we talked about before with our river example, so once particles have been transported into a new area, they must be transformed from a collection of those loose sediments into a new solid rock. So this process is called lithification. Before we get into lithification fully, because it goes a little bit more in depth, do we have any questions about the previous steps? Alright, so lithification is the combination of two processes, compaction and cementation. So compaction occurs when sediments are squeezed together. So freshly deposited sediments tend to pile up on one another, like our river example. The river goes into the ocean and loses velocity, eventually losing its sediments. So, for example, if, let's say, we'll talk about the first step, when it loses gravel. The gravel comes together and kind of stacks on top of each other, and due to the weight, it kind of, with the help of tiny particles of silts and clays, kind of squeeze together and form together, and typically also contain a lot of, or little airspace due to them squeezing together. So as they're squeezed together, their rough edges and irregular shapes tend to catch on each other and lock the mass together. And so, you guys remember our conglomerate in class that we took a look at, that's a great example of compaction. Cementation occurs when particles are glued together by other minerals. So these minerals, cements, are formed from the recrystallization of ions in a solution. So for example, my example of limestone getting eaten away by acidic rainwater. So common mineral cements are quartz and calcite, and also iron oxide, which is essentially rust. If you remember from our example of red sandstone from class, that sandstone was formed together probably by most likely compaction, but also through cementation because of the iron oxide within it. Next, we have the lithification of dissolved ions. So it's possible for ions to be dissolved in water and then undissolved to turn into new minerals. And this mass is called, or the formation of this is called precipitation. It may occur either inorganically or organically. Inorganic precipitation is often produced by evaporation. So on a hot day, if you have a pool of water that has a ton of quartz ions in it, the water eventually evaporates away, and since it can't take the quartz ions with it, it leaves them behind. And next we have organic precipitation, and this occurs from biological activities. So many organisms have the ability to remove dissolved ions from a solution, and these ions are used to build hard mineral structures such as shells with sea life, and also with for teeth and bones. When an organism dies, then their hard parts drop off to the bottom of the ocean. For example, seashells and stuff like that. If you remember our shell limestone from in class, that's an example of a rock being formed from the hard parts of an organism. Right. And next, we'll talk about the classification. I don't think that's on here. Didn't realize there were slides.
Feel it.
No. We'll get into the important rocks right here. But anyways, sedimentary rocks are classified by either elastic or chemical. Elastic rocks are rocks that are formed by fragments of other rocks. So typically mechanical weathering. And chemical sedimentary rocks are formed by the precipitation of dissolved ions out of the solution by organically or inorganically. Chemical sedimentary rocks are typically classified by the minerals that they contain. So these are some important ones that I talked about before. Didn't really cover shale, but we will. Conglomerates, they are formed primarily by gravel. You want to classify a rock by the majority of its sediments or particle size. So with a conglomerate, conglomerates contain over or at least 51% gravel. So when talking about its particle size of a conglomerate, it is gravel size. Sandstone, our example of red sandstone, contains at least 51% sand, so that's why it's classified as a sandstone. And our shale, because it is sometimes hard to tell silts from clay due to their very small particle size, if they contain at least 51% of silts and clays, they're classified as shale. Anything else? Dissolved ions, we already talked about sandstone, elastic and chemical. And if you remember from Lab 3, we talked about the definition of a rock. To paraphrase, a rock is a combination of minerals that occur inorganically. So bituminous coal is a contradiction to that. It is formed from sediments and bits and pieces of woods that have accumulated in stagnant water. So when they fall into the water does not have enough oxygen to support microbial life. So the microbes aren't able to eat or break down the old wood, so it just sits there for a while. Eventually, more sediments pile up on top, and some of the other minerals and parts of the wood kind of deteriorate away and leave behind carbon. And that is how the sedimentary rock bituminous coal is formed. Any questions on sedimentary rocks?
How's it, Jeff?
All right. Next we'll have Mr. King with Lab 5 volcanoes.
All right. Let's last one. Almost there. So let's talk about volcanoes. Talk about volcanoes in your lab annual. It is page 37. So a lot of the rocks that Dexter discussed were formed through volcanoes. So, why do volcanoes erupt? Well, something that I do for my students, if you're any of my students, do the same here, is I take a bottle, right? And imagine this bottle is a volcano. I specifically chose orange Fanta because, magma, it's cool. Anyway, so when you build up pressure, when you take this bottle, you shake it, you build up the pressure. What happens is the gases inside this soda bottle start to build up. So if I were to possibly open this, I'm not going to do that right here, although I do in class typically, the contents of that soda bottle would explode outward through the only way that they are able. And if this Fanta bottle were a volcano, the top of this would be the lava chute, would be the main lava vent, right? And this functions much in the same way, where gases build up so much pressure within the magma, within the lava. We'll get to the difference between magma and lava, but there is still some lava in there. That it starts to push everything outward. push everything outward. And when that pressure builds up to a point that it can no longer sustain itself, it can no longer sustain a stable environment, it explodes. The pressure is released. So magma, remember the difference between magma and lava is magma exists beneath the surface of the earth, right? Magma is molten material that is yet to be extruded, and lava is molten material that has found its way to the surface, right? But magma contains molten rock and gases. So as it says on the slide, when the pressure becomes too great, an eruption occurs. So like when I shook up this bottle, and if I were to open it, the contents would erupt upward and outward. And as it says, most eruptions are actually composed of ash and water vapor. All right. So the lava that finds its way out. Lava that finds its way out. You might think that, well, it's just molten material, right? But no, there are different types. There are different types. We have three types. We have the right? The okay? The hohoi, and then we have the pillow lava. The pillow lava. The last one doesn't sound as inspired as the first two. But, all right, so let's get into these. So the and these are words that were coined by people in Hawaii, okay? The is lava that is basaltic in composition. So it has high viscosity. High viscosity. So therefore, it is thick, right? So I think we talked about, yeah, it even says here, it's like jello. It's like jello, right? So imagine trying to get jello to move through something. It would move slowly. It would meander its way. And what it would manage to make contact with, it generally gets kind of sticky, right? And it's typically lower in temperature, although we're talking about low in temperature, we're talking about 1,000 degrees C here to 1,100 degrees C, so relatively cooler compared to hohoi. So low in viscosity, so that means it moves and it flows quickly. So if we were to again look at this fancy bottle, right, and you were to see that I can very easily move the liquid, okay? So this volcano of a soda bottle would have hohoi lava because it flows very easily. But also, this lava would be very hot. Would be very hot, 1,100 to 1,200 degrees C. That does not seem like that big of a difference from the but it is. Also, keep in mind, we are talking about Celsius here, so typically we're used to Fahrenheit, but as I say in my class, we're speaking the Queens here, so we are charting things in Celsius. So yes, this is a different scale and much hotter. But then we have pillow lava. So imagine there's a volcanic bed underwater, and again, we come back to Hawaii. I often bring many of my classes back to Hawaii to talk about this, is that a lot of the lava bursts up through these hot spots, right? It doesn't erupt properly, as you would expect, but instead, the lava reaches the surface and is immediately caught in water, right? And it tends to create these, like, shells. Okay? So as Dexter mentioned in Igneous Rocks, is when you have liquid material or molten material that hits water, it is instantly cooled. It is instantly cooled. So one of the ways we talk about this is the crystals are fused together, right? And this is what happens here with the pillow lava, is basically this lava is extruded into the water and then it just fuses other lava within that, like, encase it, right? All right. We talk about hot spots and stuff here. Oh, back here. Okay. We're gonna make a real quick detour here. Volcanoes are formed. This is the book, and I'm pretty sure there's a question here. Are there questions about subduction and hot spots in the? Let's see. Because we're gonna just talk about this real quick. So volcanoes are formed through two different methods that we're gonna talk about today, and we have subduction. Subduction. So this occurs when two plates meet one another, two tectonic plates meet one another, and one subducts beneath another. And what happens is when one subducts beneath another, the plate that has subducted is thrust into the earth, and the deeper you go into the earth, the hotter and more pressure is built up, and it starts to melt, and the lava rises, and eventually forms a volcano as that lava, so that magma is pushed through the earth. And then you have hotspots. So imagine if you were to lay a piece of paper, right, on this table, and you were to move the piece of paper. Okay, but every now and again, you would drop something on it, right, as it's moving. That is the way that islands can form, or certain volcanoes can form as it moves over a spot of magma that is being pushed up through the mantle. Okay? And this is one where, again, we really don't talk about volcanoes without talking about Hawaii in my class, because it is such a volcanically active place, and it gives us a really good look into the history, and you can see that the islands are almost like a nice, perfect chain, and you can watch how the hotspot has formed each one of the islands over time as the tectonic plate has moved. All right, but now let's get into the volcanoes themselves. Are there?
No questions in chat.
Darn. It's cool. We got there. All right. So let's talk about cinder cone volcanoes. So, if you're talking about cinder cones, there are 3 types of volcanoes, and we're going to start with this one. This is the one where when you're a kid, you want to draw a volcano. You just draw like a typical like sloped mountain, and then it's got like a little bowl at the top, right? And this is one they call a cinder cone because a lot of the rocks and stuff that form at the top in the bowl look kind of like cinders, or tend to be rough or porous, right? And these typically are not very tall, usually about 1,000 to 1,500 feet. And here you see a nice picture of one. All right, into composite volcanoes. So these composite volcanoes are really big. And they tend to be really towering volcanoes. And I think in my class, I showed my class the picture of Mount St. Helens when it exploded. And basically, these are large enough that the entire side of the mountain can just be completely thrust outward through the release of pressure. And it just obliterates anything in its way. They're also straddle volcanoes because of how high they can get. And these are typically symmetrical, but very steep. They are very steep. And they have a central vent. So this, we're going to come back to the phantom bottle again, would be a typical cinder cone volcano, but if it would be a composite volcano, I would maybe like want to put some holes in the side so it would have areas where the lava could come out. Right? But as volcanoes, composite volcanoes have these vents, but they also have fissures and dikes that go throughout the volcano itself. Last but certainly not least, is a shield volcano. So if you have seen pictures of a massive volcano on Mars, you have seen the largest volcano in our solar system. And shield volcanoes are volcanoes that what happens is the magma is extruded, and as it hits the surface, it slowly spreads out. And over time, it builds, and it builds, and it builds, and it builds, until you have a very tall and wide volcano. I think it says these things can sometimes be 3 to 4 miles across. So they can be absolutely enormous. So, cinder cones, typically 1,000 to 1,500 feet, your normal looking volcanoes. And then you have the composites, which are stratovolcanoes, which means they can reach really high in the atmosphere and have multiple ways for the magma to reach the surface. And then the shield volcanoes, which slowly build over time and tend to be not only very tall, but also very wide. All right. Any questions? As that is the end of the 253 review. Any questions? All right. Well, students, best of luck on your midterms, and Dexter and I will be here if you have any questions for us, but good luck. Have a nice time.